Good morning all. In this video lecture, we are going to solve one numerical for the spring and mass system. We need to calculate the natural frequency of the system. Then what is the problem here? You can see the natural frequency of the system, right? And what is the given the figure here? There we can see the two springs, they are going to be connected parallel, and they are connected to the one end is connected to the mass, and the third spring they are attached over here. So this is the arrangement of the figure. That's we need to be calculating the natural. So to this system we need to calculate the natural frequency. Then what is the data he has provided for us? The data is given here. The K1 and K2 is equal to 1500 Newton meter. The K1 and the K2. These are the K1 and K2 are the spring stiffness of the 1 and 2 springs, right? And K3 they given 2000 Newton meter. And here is the K3, the third spring stiffness constant is going to be 2000 Newton meter. And the mass of the system they given around the 5 kg. So in this case, so this is the given data and this is the given figure. So then what do you want to calculate from this one? So the calculation part is going to be the natural frequency. That is going to be F we need to calculate. So then what is the F formula we do have? So first we are going to be trying to analyze what you want to calculate and what parameters we require. So that's F is equal to natural frequency. F is equal to, what's the formula here? That is going to be omega n by 2 pi formula we do have. So in this case, so that is equal to 1 by 2 pi square root of k by n. Right? This is the natural frequency when we have a single spring and a mass. But in this case, we do have a 3 springs are there. So then what we are going to do? That's in this case, I am going to be taking the equivalent stiffness of the spring. That is the combination of all these 3. Then I am going to be calculating the natural frequency of the system. So then how could you calculate here the equivalent stiffness of the spring? In the last classes, we have seen that how to convert parallel springs into a equivalent springs and the series connected springs, how to connect it into the equivalent stiffness of the spring. So first I am going to be taking this figure and I am going to be converted into the equivalent spring system. So then what happened? The K1 and K2 they are in the parallel condition. So that's I am going to be taking here. This is the mass. This is the third spring we do have. This is I am going to say KE. KE is going to be the equivalent spring for these parallel connections, and this is going to be the K3. The KE is equal to K1 plus K2. Right? That's we got it. And how we are going to be converted KE? Here I am going to say 1, 2 because I have used the spring 1 and spring 2. But now I am going to be taking the 2 springs are there in this system. And then how could you convert it? So I am going to be simplifying this one. So by assuming that here, when the spring is going to be start to move in the downward direction, the deflection of the spring in equivalent spring that is equal to the deflection of the spring 3. So that's we can going to be. So here that force we are going to be applied. Then what happened? This mass is going to be trying to move in the downward direction. The deflection here, the spring 1 is going to be elongating and another spring is going to be compressing. That is going to be elongation is going to be the equal to the compression of the spring. So simple that I am going to be taking here. That is the M. So the total equivalent spring I am going to be saying the KE. The KE is equal to what is the formula? KE 1 2 plus K2. So on that basis, I am going to be calculating the equivalent stiffness of the system, and then I am going to be substituting in this equation. I can calculate the F. Right? So now you come to here. KE1 is equal to what is the formula? That is the K1 plus K2. So that as we know that K1 is equal to K2 is equal to 1500. So equivalent spring constant KE12 is equal to what is the formula? K1 plus K2 that is equal to 3000 Newton meter. And similarly, we need to calculate the equivalent spring constant. That is going to be the Ke is equal to Ke12 plus K3. So then what happened? Ke12 is equal to 3000 Newton meter and K3 is equal to 2000 Newton meter. Then totally it is going to be 5000 Newton meter. We got it. Right? And we got the 5000 Newton meters. And here is the mass is going to be the 5 kg. And this is going to be the 1 by 2. And finally, once I am going to substituting F is equal to 1 by 2 pi square root of 5000 by 5 kg. So here, after this, substituting in this equation, the finally we are getting the 31.62 by 2 pi value, and then after simplification, the natural frequency of the system, that is equal to 5.03 Hz. Right? In this case, the summary of this equation, the summary of this problem is that, so they given, we need to find out the natural frequency of the system. Then what the kind of system it is? It is the combination of the different springs they are given. So two springs are above the mass and one spring is going to be below this one. So then these two are in the parallel condition, that I simplify into this two springs mass system. Then the two springs are going to be converted into the single spring mass system. So then the Ke is equal to Ke12 plus K3. And we are calculating here is what is the Ke12 and Ke. Then I have substituted in the frequency F is equal to 1 by 2 pi square root of omega n. So that is going to be square root of Ke by m. Then finally we got the natural frequency for this system is equal to 5.03 Hz. Thank you. I hope you understand.